Hi, I'm Xinyu, and I'm going to be telling you about explicit near-fully X-Ramanujan graphs. This paper is joint work with Ryan O'Donnell at CMU. So this paper is about infinite graphs, and here's a picture of my favorite infinite graph, a D-regular infinite tree. In particular, here is a 6-regular infinite tree, which is denoted T6. And here are some yet more interesting pictures of infinite graphs that will be covered in our setting. And in general, we'll be considering infinite graphs with some sort of repeating pattern, as in the graphs here. The main theme of this work is that for all of these infinite graphs, I want to be able to construct finite graphs which somehow resemble the infinite graphs. And this resemblance should happen in two different measures of similarity. So the graphical structure of the finite graph should look like the infinite graph in terms of the local neighborhoods. And I also want the spectrum of the finite graphs to look like the spectrum of the infinite graph. Let me now just give you a very broad overview of what this goal is all about. So for this talk, I won't be extremely precise with all of the definitions. Instead, I'll just go over all of the ideas informally. And so the question of whether we can find finite graphs which resemble the spectrum and structure of infinite graphs is actually a pretty natural question to ask. We do know a classical situation where this goal has already been achieved. So it's been achieved by deregular Ramanujan graphs. Ramanujan graphs are just graphs which have non-trivial eigenvalues with magnitude at most square root d minus 1. And in this sense, they are the best possible spectral expanders. So Ramanujan graphs structurally look like the infinite deregular tree in the sense that the deregular graphs look like local pieces of the infinite deregular tree. And their spectrum also resembles the spectrum of the infinite deregular graph because 2 square root d minus 1 is the spectral radius of the infinite deregular tree. So you can really think about this statement about the spectrum as a statement relating the finite graphs to the infinite deregular tree spectrum. And of course, expander graphs are super important in CS theory. They have many applications, for example, in pseudo-randomness and error correcting codes that I won't go into in this talk. And we also know many explicit constructions of Ramanujan graphs. For example, in the classical work of Margulis and Lubotsky, Felixstoner, and Morgenstern, where they have algebraic constructions of Ramanujan graphs for d minus 1 being a prime power, where d is the degree of the graph. And also Marcus Wilman's Shirasawa has a construction for bipartite graphs, which has been made explicit in the paper of Cohen. So for this paper, we'll be going at this with a slightly different angle. And it turns out that randomized constructions actually work very well for this goal of finding finite graphs which resemble infinite graphs. So we'll be looking at random deregular graphs. So for example, a random deregular graph can just be constructed by summing up the uniformly random matchings. And it turns out that random deregular graphs actually they turn out to resemble the infinite deregular tree because the local neighborhoods of a random deregular graph look like local pieces of the infinite deregular tree. And also by a conjecture of Alon that was proven by Friedman, the random deregular graphs also spectrally resemble the infinite deregular tree in the sense that it is up to like epsilon, it's almost Ramanujan. And this happens with high probability. So a main part of this paper is trying to find explicit graphs that satisfy this sort of almost Ramanujan property. So this Friedman's theorem, there's an alternate proof given by Bodanov, and that proof was made explicit in the recent paper of Mohanty, O'Donnell, and Paredes. And this paper is going to generalize this sort of work. Okay, so that was for deregular trees. So now it's not too crazy to ask. So how do we find finite graphs which resemble non-tree infinite graphs? So for example, you might want to consider an infinite graph where every vertex is part of both a four-clique and a triangle. And I've drawn like just 2 layers of this graph here. You can imagine that it extends out infinitely. So I want to find some finite graph that also locally has this property. So it also has the property that every vertex is inside both a triangle and a four-clique. And then I want this finite graph to have the best possible spectral expansion. So an interpretation of this is that I want to find a expander that has some local constraints on what the structure looks like. Yeah, so, well, you can think of, okay, so this kind of graphs do come up in computer science. For example, if you look at the random constructions, then this type of graph shows up as typical instances of random constraint satisfaction problems. And if you look at the finite graphs, it can be thought of as the constraint graph of a set instance. And then looking at the eigenvalues of that graph will tell you something about whether the instance is satisfiable. So there's so many more details here that are covered in our paper, but I'll just leave this as some sort of motivation. Okay, let me talk a bit more about what it means to spectrally resemble an infinite graph. So if I have this graph again, the eigenvalues look like this on the number line. So you might be used to looking at the eigenvalues as like a histogram of the distribution, but here I'm literally drawing the just the support of the eigenvalues. So if you look at the infinite graph, there's going to be eigenvalues at -2, at 3, and in these two intervals that I've drawn. And yeah, because the infinite graph has like a continuum of eigenvalues, has like infinitely many eigenvalues. The eigenvalues are literally going to be intervals. It's not too important exactly what the intervals are, but just here there's going to be 2 intervals and 2 points. So when I try to find a finite graph, I want it to locally, structurally look like this infinite graph. And then I want its spectrum to have this support. So it should also match this -2 and 3 here. And then it should have finitely many eigenvalues. And the eigenvalues should basically fill out these intervals that are part of the infinite graph. And so I drew these points sort of evenly spaced apart, but of course they don't necessarily need to be. Basically, what I'm looking for is just there should be at least one eigenvalue in every like epsilon interval, and then it should not like go beyond epsilon of like the bounds of the infinite graphs spectrum. So in the recent paper of Bonhoff and Collins, they gave a randomized way to construct finite graphs that satisfy this. And our work here is to de-randomize this proof. All right, I'm not going to be able to present all of the details of the construction, but for the rest of the talk, I'm just going to give you one key idea from the paper of Bonhoff and Collins. So we want to approximate all of these infinite graphs with finite graphs. And the first obstacle here is, of course, how do we even concisely represent the infinite graph that we're trying to approximate? So the first step is to come up with some way to represent the infinite graphs. And the way we're going to do it is like to have this algebraic recipe that represents all of these infinite graphs. So the idea of using this representation is from the Bonhoff-Collins paper. Although if you read that paper, it might not be immediate that they're talking about this, and because I'll be presenting it in a slightly different way. And eventually we'll see that this kind of algebraic recipe can be used to describe lots of different infinite graphs. And part of our contribution is investigating which graphs can and cannot be produced with this sort of recipe. So I'll step through this idea with a couple of examples, starting with just the infinite 6 regular tree. Okay, so back to this example. What I'm going to do next is I'm going to color each of the edges of the tree in such a way that I can view the graph as the sum of 3 different colored lines. So there's the green edges and the blue edges and the purple edges. And I'm coloring this in such a way that the structure appears at every node. So in the sense that I'm looking at this 6 regular tree as a color regular graph. At every node, there's going to be 2 blue lines and 2 green lines and 2 purple edges. And so in addition to putting the colors on the edges, I'm also just going to put a direction. The direction is just for illustration. I'm still eventually going to look at only the undirected infinite tree. So just putting these directions is just a step in the algebraic representation. So now at each node, there's going to be one edge of each color going in and going out. Okay, so let's just focus on the green arrows. the green arrows actually define sort of a permutation on the vertices of the tree, in the sense that if you take every vertex and you move it along the green arrow, that's going to be a graph automorphism. So you can think of this as, you can think of the green arrows as defining an infinite like cyclic permutation of the vertices. And the same thing holds for the blue and the purple edges. And so you can think of that as being like 3 different permutations, the green, blue, and purple permutations. And then when each of these permutations define some edges, so the 6 regular tree is just going to be the sum of these 3 permutations. And yeah, I'm just going to use G1, G2, and G3 to represent these permutations. So with the 6 regular tree, this is just going to be G1 plus G2 plus G3. So eventually we want to think about the 6 regular tree as being an undirected graph. So we're also going to add in the inverse permutation. So that's why I've added G1 inverse and G2 inverse and G3 inverse here. The proper like terminology for what I'm doing here is that I'm viewing the 6 regular tree as like the Cayley graph of the free group on tree generators, and the generators of the F3 are exactly G1, G2, G3 here. And you can also think of the free group of tree generators as the free product of 3 copies of C. Okay, let me be a little bit more precise about how the 6 regular tree is supposed to be the sum of permutations. So if you look at each generator, you also can have a matrix representation of it. So this is just going to be the infinite permutation matrix that's the representation of the generator. And then when you take the green, blue, and purple permutations, and then you sum up the permutation matrices that represent the generators, this is going to give you an adjacency matrix, and that's the adjacency matrix of the infinite 6 regular tree. So for these permutation matrices, just note that the adjoint of the permutation matrix is equal to the inverse, which is also equal to the permutation matrix of the inverse generator. So that's why I'm adding in the adjoints of the permutation matrices as well. And now we can make an abstraction. I want to view this sum not just as a sum, but as a formal polynomial. So this polynomial is just going to be the sum of 3 variables and their adjoints. And you can recover the adjacency matrix by just plugging in P or the permutation representations of G1, G2, and G3 into the X1, X2, and X3 respectively. So yeah, so I guess as a point of notation, I'm going to avoid I'm just going to omit using the capital P's for the rest of the talk and sort of just identify the permutations with the generators. And one more thing to note here is just because my polynomial is formally self-adjoint in the sense that for every term, the adjoint of the term also appears. Then when I plug in these permutation matrices, it's going to result in an undirected graph. So like for this paper, we mostly only consider self-adjoint polynomials, and because we want to eventually just study undirected graphs. Okay, so I went through all of that business of viewing the graph as a polynomial because then it lets us think about more general polynomials and how that can represent more general graphs. So for example, let's look at this degree 2 polynomial and what happens when we plug in 2 generators or like 2 infinite permutation matrices. So it's not actually obvious what's the graph you're going to get. And really the only way I know how to figure out what graph a polynomial generates is to try and draw the graph on a piece of paper. And at this point, I'll just encourage you to pause the video and take out some pencil and paper and try and figure it out. Okay, so let's make a couple of observations about this polynomial. So because there are 2 variables and we're plugging in 2 different generators, the vertex set should be the free group on 2 generators, which are equivalently, it's the 4 regular infinite tree. And then because there are 3 terms and their inverses, the graph that we're going to get should be a 6 regular graph. And now the terms will determine what the graph actually looks like. So I have this polynomial again, and after I plug in the generators, I'm going to end up with this infinite graph. So it's going to be the infinite graph where every vertex is going to be inside it, participating in 3 triangles. And here I've colored the edges of the graph so that you can see which terms correspond to which edges. So the way I would think about it is that I would look at x1 and x2. So that's the blue edges and the purple edges. So that's going to define a 4 regular infinite tree. And then the x1, x2 term sort of means that whenever you take x1, you take a step in the x1 direction, and then you take a step in the x2 direction, you should join those vertices with a green edge. So after you do that, you're going to end up with this graph. This is the graph that you're going to end up with. So it turns out that this sort of permutation mechanism can generate lots of other cool graphs, and I'll go into more detail later about what exactly you can do with these polynomials. Okay, so next, let me talk a little bit about how we're going to find finite graphs that resemble the infinite graph. So the main approach here is, well, we had all of these infinite permutations. So the natural thing to try and do is just what happens if we replace the infinite permutations with some finite permutations. So, well, we can, for example, just take finite permutations on n elements, and then we plug that back into the polynomial. So for our example, there was just the sum of x1, x2, and x3. Then when you plug in some finite permutation matrices, that's going to give you the adjacency matrix of a 6 regular graph on n. And so we'll also be considering doing this with random permutations a lot. So when you do that, you just end up with a random 6 regular graph. And here's our other example of the polynomial. And what happens when you plug in some random permutations here is that you get this finite random graph. And the thing that happens is that the finite random graph also has this structure where there is like 3 triangles at every vertex. So if you compare this with the infinite graph, it locally looks like the vertices of the infinite graph. And you might notice that some of these neighborhoods don't actually look like they have 3 triangles. For example, there are some self loops and there are some double edges. But the key is really that we have to define our notion of approximation such that these nodes are also going to be counted as resembling the infinite graph. And if you really were worrying about them, you should also just understand that the number of such self loops, it goes to 0 as n goes to infinity. And also, if you really cared about that the constant size neighborhoods of the finite graphs are exactly isomorphic to pieces of the infinite graph, this can also be shown. Okay, so now we have a way to identify formal polynomials with infinite graphs, but still with the polynomials we had, we could only make regular graphs. So how can we generalize this to get irregular graphs? So one direction to try is, now that we have some algebraic way to describe the infinite graphs, let's try and make some algebraic generalizations to the polynomials. So one natural thing to do is to add coefficients and look at what this does to the graphs. So this is exactly what Bornoff and Collins did. And they didn't just add scalar coefficients, they added matrix coefficients. So for example, I can have this polynomial that's just a1 x1 plus sum to ad xd plus the adjoints of those. And the a's here are going to be matrices. So you can basically think of them as being 0, 1 valued if you're going to eventually consider like unweighted graphs. Then the way that I would evaluate this polynomial on permutations is that when I plug in the permutations into the polynomial, I would tensor product the permutation matrix with the coefficients. And then so this is an operation that is independent of the dimension of either the coefficients or the polynomial or the permutations. And after I do that, I would interpret this matrix as the adjacency matrix of a graph. And it turns out that that's going to let you describe a super wide variety of graphs, including all of these here. So Bornoff and Collins proved that for any such matrix polynomial, if you replace the infinite permutation with a random permutation, that would result in a graph that locally looks like the infinite graph, and the spectrum also converges to the infinite graph spectrum, except the trivial eigenvalues. And this convergence happens with high probability in the very strong sense I talked about, which places every eigenvalue exactly where it's supposed to be. So for our results, the first part of our paper investigates what infinite graphs the matrix polynomials can generate. So in Bornoff-Collins' paper, they only use it to generate these things called universal covering trees, but we additionally show that matrix polynomials can be used to describe all sorts of graph products in the literature, including free products of vertex transitive graphs, these additive products, and amalgamated free products. And we also show some necessary conditions for a graph to be representable by a matrix polynomial. So for example, the infinite graph needs to be hyperbolic, and it has finite tree width, and also have a unimodular automorphism group. And the second part of our paper is we prove an explicit form of Bornoff-Collins theorem. So given some matrix polynomial and some epsilon, we have a polynomial time algorithm that produces a graph that it locally looks like the infinite graph, and it also spectrally is close to the spectrum of the infinite graph in the same sense as I mentioned before. All right, so let me finally just finish up with some open problems. So firstly, I guess we don't yet have a complete characterization of which graphs can arise as matrix polynomials, and it would be interesting to try and connect this to other sorts of algebraic like descriptions of graphs. And then, so the finite graphs that we generate, the non-trivial eigenvalues are not fully contained in the spectrum of an infinite graph. They are like within an epsilon. So you could also ask, can we find finite graphs that are whose spectrum are entirely contained in the spectrum of the infinite graph? And of course, it's also going to be cool if we can look at further applications of this kind of expanders with local constraints in various PCS applications. All right, thanks.